Spring 1943, eastern edge of the Libyan desert. The German engineering officer stood motionless, the blueprint tube clutched tight against his side, as British Major Alan Macfarlane explained the unexpected proposal. "We need a Bailey bridge across this wadi in 48 hours, Lieutenant. Your expertise could save lives. Both sides." The German's eyes narrowed in suspicion. After months building defensive fortifications for Rommel's Afrika Korps, then enduring capture and processing as prisoners, this request defied everything Nazi propaganda had prepared him for. British captors weren't supposed to ask for engineering collaboration. They were supposed to interrogate, isolate, perhaps even execute officers. The reality unfolding across North Africa in early 1943 would systematically dismantle German assumptions about British military engineering and prisoner treatment. Throughout that spring, 1,142 German military engineers from Rommel's defeated forces would confront a reality that contradicted everything they'd been taught about British technical incompetence and brutal prisoner treatment. They discovered captors who recognized professional credentials, respected technical expertise, and most shockingly, requested collaborative assistance on critical infrastructure projects. The professional courtesy extended to German engineering officers, complete with access to drafting tables, calculation tools, and technical consultations, would ultimately undermine Nazi ideological certainties more effectively than any propaganda campaign. The mathematics of respect was being written in bridge spans and load calculations, in stress tolerances and foundation designs, revealing a British approach to warfare that rendered German assumptions not only incorrect, but fundamentally misguided. What began as bewilderment at British pragmatism would evolve into complete psychological transformation. Desert's End. The surrender of German and Italian forces in Tunisia during May 1943 brought approximately 130,000 Axis troops into Allied captivity. Among these prisoners were 2,184 members of German engineering battalions, men who had constructed Rommel's defensive positions, maintained supply routes, and designed fortifications across North Africa. These specialized troops, who had regularly repaired bridges under British bombing, expected harsh punishment as high-value prisoners. Nazi security briefings had prepared them for interrogation focused on German engineering techniques, construction methods, and material specifications. Instead, within days of processing, they encountered British engineering officers carrying Bailey Bridge manuals, foundation specifications, and structural calculations. Captain James Winterbottom of the Royal Engineers later recorded in his field journal, "The Germans appeared genuinely stunned when I consulted them on abutment specifications rather than interrogating them about their previous work. Their expertise in rapid bridge deployment under combat conditions precisely matched our immediate needs." The systematic engagement of enemy expertise began immediately, though its psychological impact would only be understood later. A German engineering lieutenant later testified to the International Red Cross, "We expected to be treated as security risks, perhaps even saboteurs. Instead, the British officers consulted us as fellow professionals. This confusion about professional respect began our re-education. The transportation of engineer POWs to specialized holding facilities throughout May 1943 provided intensive education in British military engineering. These smaller camps, established near critical infrastructure needs, housed between 20-50 German engineers each, supervised by British Royal Engineers officers. Military records show these facilities maintain standards exceeding Geneva Convention requirements, providing drafting tables, technical reference materials, and even slide rules, precision calculation devices worth approximately $8 each, equivalent to 2 weeks' officer pay. Most remarkably, documented accounts confirm that German engineers received regular briefings on bridge requirements and specifications. Captain Winterbottom's June 1943 report notes, "The German engineers rapidly adapted to Bailey Bridge specifications, once shown the prefabricated panel system. Their initial skepticism about the modular design gave way to professional admiration when load capacity calculations were verified." When engineering teams began the field deployments, German prisoners encountered a British military engineering approach that Nazi propaganda had declared technically inferior. The Bailey Bridge system, developed by British engineer Donald Bailey in 1940, could be assembled by relatively unskilled troops under combat conditions. Its modular design, with identical interchangeable panels, required minimal specialized equipment. A standard 100-foot Bailey Bridge could support 40-ton tanks, yet be assembled by 40 men in under 6 hours. German engineers, trained in custom-designed fixed structures requiring specialized materials, initially dismissed the Bailey system as primitive. Technical specifications revealed otherwise. Each bridge panel, precisely manufactured to tolerances of 1/64 inch, could bear 70,000 pounds of compression force. Engineering officer Carl Miller's diary, recovered after the war, recorded his astonishment. British panel design exceeds our best prefabricated systems. Each connection point distributes load stress with remarkable efficiency. We have nothing comparable in our inventory. The respect demonstrated to German engineering officers delivered the deepest impact. According to Royal Engineers records, captured German officers received consulting status, reviewing plans, suggesting modifications, and eventually supervising construction teams. They were addressed by rank, invited to planning sessions, and their technical suggestions were implemented when proven sound. This professional acknowledgement, offering enemy officers respect rather than humiliation, contradicted everything Nazi leadership had predicted about British behaviour. As spring turned to summer, the first Bailey bridges designed with German consultation spanned wadis and gullies across the North African theatre. Each structure, rapidly deployed yet surprisingly durable, became a physical manifestation of unexpected collaboration, enemy expertise now advancing the Allied cause one bridge at a time. Summer 1943. Sicily's rugged eastern coastline. German engineer Lieutenant Werner Schmidt watched with professional intensity as British sappers bolted Bailey bridge panels over the Simeto River. His critical eye noted details: panel pins driven with precision, cross braces tightened to exact specifications, span calculations allowing for thermal expansion. 3 weeks earlier, Schmidt had been a prisoner expecting interrogation. Now British Captain David Morris consulted him on foundation stability for a bridge that would carry Allied tanks toward Messina. "We've encountered unexpected bedrock at the south abutment," Morris said, unfolding detailed survey maps. "Your experience with similar conditions along the Libyan coastal roads would be valuable." The British officer's tone carried no irony, just professional respect for technical expertise that transcended battle lines. What began as an expedient solution in North Africa transformed into a strategic advantage during the Sicilian campaign. As Allied forces advanced across Sicily in July 1943, they faced 251 demolished bridges, each requiring rapid replacement to maintain momentum. The British War Office's initially reluctant experiment with German engineering consultations had proven so successful that Field Marshal Montgomery personally authorized expansion of the program. War Office Memorandum WO 2265, dated July 19, 1943, noted, "German engineering officers have demonstrated exceptional value in bridge replacement operations. Their familiarity with demolition techniques employed by retreating Axis forces enables more rapid assessment and countermeasures. British engineering officers discovered unexpected advantages in professional collaboration that crossed enemy lines." Major William Hartley recorded in his field journal, "German engineers approach problems with methodical precision that complements our more improvisational tendencies. Their calculations regarding load distribution across compromised foundations have proven invaluable." This technical respect gradually evolved into cautious professional camaraderie. Captain James Wilson noted, "One finds oneself in the odd position of discussing pre-war civil engineering projects with men who were, just weeks ago, ensuring our tanks couldn't cross these same rivers." Living conditions for German engineering consultants reflected their unusual status. Neither traditional prisoners nor free men, they occupied a professional middle ground unknown in modern warfare. Royal Engineers documentation shows these specialists received accommodations in Engineering Corps quarters, ate in officer facilities, and worked alongside British counterparts in planning sessions. They remained under guard, but guards were instructed to permit free movement within technical areas. German engineer Captain Karl Heinz noted in a censored letter home, "Our status here defies understanding. We wear prisoner uniforms but attend daily briefings with British officers who solicit our opinions on structural questions." The contrast between Nazi propaganda and observed reality created profound cognitive dissonance. German officers raised in the Speer engineering tradition, which emphasized rigid hierarchical authority, witnessed British engineering teams operating with delegated authority and collaborative problem-solving. Lieutenant Schmidt's diary entry from August 1943 revealed growing confusion. British engineering officers openly debate technical approaches with subordinates, even accepting corrections from sergeants with practical experience. This contradicts everything we've been told about British-class rigidity and inefficiency. The Bailey Bridge itself became a powerful symbol of contrasting approaches. Developed by civil servant Donald Bailey, the system represented British pragmatic innovation. Simple, adaptable, mass-produced. German engineers, trained in custom-designed structures requiring specialized materials and skilled labor, initially viewed the modular system as primitive. Technical evaluation revealed otherwise. Each Bailey panel weighed exactly 600 pounds, requiring 6 men to carry, yet interconnected to span rivers that would have demanded weeks of German custom construction. Royal Engineers historical records document the precise scale of the collaboration. By September 1943, approximately 87 German engineers were actively consulting on bridge projects across Sicily. Their contributions included 132 technical modifications to standard Bailey designs, addressing unique terrain challenges. British production had reached unprecedented levels, with factories in Wolverhampton and Manchester producing 20 miles of Bailey bridging monthly, enough to span the English Channel. German engineers, accustomed to material shortages, witnessed supply chains delivering hundreds of identical panels to remote locations within days. The effectiveness of this unusual collaboration prompted official expansion. War Office Directive WO 215/79 authorized formation of specialized German engineering advisory units, GEAUs, each comprising 15 to 20 German officers under British command. Their status remained ambiguous, prisoners providing voluntary expertise that advanced Allied progress while hastening German defeat. International Red Cross inspections noted the arrangement's unprecedented nature, but found no violations of prisoner treatment protocols. The German High Command, upon learning of the program, declared participating officers traitors, yet could not deny the pragmatic British approach demonstrated resourcefulness they had never anticipated. As summer ended, the impact of these collaborative bridges extended far beyond tactical advantage. Each successful span represented a psychological bridge between opposing worldviews. German engineers raised in a system that equated strength with rigid control, encountered British officers who displayed strength through adaptation and collaboration. Every completed bridge, many constructed in under 24 hours, challenged fundamental German assumptions about British capabilities. Most significantly, German engineers observed that recognition of expertise transcended national boundaries in British military culture, directly contradicting Nazi claims of British contempt for German technical achievement. By autumn 1943, as Allied forces secured Sicily and prepared to cross to mainland Italy, dozens of Bailey bridges stood as physical manifestations of an unexpected truth. Respect for professional competence had created working relationships between enemies that no propaganda could have predicted or prevented. Each bridge carried Allied vehicles toward Berlin, while simultaneously carrying German engineering officers toward profound reconsideration of beliefs they had once held certain. Winter 1943, Sangro River Valley, Italy. German engineer Captain Friedrich Weber stood ankle-deep in freezing mud, pointing to an improvised drawing spread across the hood of a British jeep. Around him, Royal engineers nodded as he explained his modification to the standard Bailey design, a reinforced centre panel system to accommodate the unusual width and current of the Sangro. "The riverbed is unstable here," Weber explained, his breath visible in the December air. "We face similar conditions near Tobruk. Your standard footings will sink unless we double the distribution plates." British Major Harrington made quick notes, asking clarifying questions without hesitation. 6 months earlier, Weber had commanded a German pioneer battalion tasked with destroying bridges to slow Allied advances. Now his expertise was being applied to accelerate those same advances, a contradiction that kept him awake at night. The Italian campaign transformed the bridge-building program from tactical necessity to strategic advantage. As Allied forces pushed northward through Italy's mountainous terrain, they encountered over 1,700 bridges destroyed by retreating German forces. The specialized knowledge of German engineers, many familiar with the exact demolition techniques employed, proved invaluable in rapid replacement. Lieutenant General Oliver Leese, commanding the 8th Army, noted in December field reports, "German engineering consultants have reduced bridge replacement timeframes by approximately 40%. Their familiarity with demolition patterns enables precise countermeasures." By early 1944, the program had expanded dramatically. British military records document the formation of 15 German engineering advisory units operating across the Mediterranean theatre. These specialized units, each consisting of 12-18 German officers and 30-40 enlisted engineers, worked under British supervision on critical infrastructure projects. Their status evolved from closely guarded prisoners to trusted technical partners, though they remained officially designated as prisoners of war. Captain James Winterbottom, who had pioneered the program in North Africa, recorded in his February 1944 assessment, "The transformation in these men is remarkable. They arrived as reluctant captives. They now function as engaged collaborators, taking evident pride in technical achievements that advance our progress." The collaborative approach produced unexpected breakthroughs. In January 1944, German engineer Major Karl Heinz proposed a modification to standard Bailey bridge designs to accommodate the wider Italian rivers. His double-double configuration, using parallel panels in both horizontal and vertical alignments, increased load capacity from 40 to 70 tons while reducing assembly time by 25%. British engineers, initially skeptical, tested the design across the Garigliano River and confirmed its advantages. The modified design was subsequently adopted as standard for major river crossings, with manufacturing specifications transmitted to production facilities in Britain. German engineers, accustomed to having their expertise dismissed by Nazi leadership obsessed with rapid production, found their technical suggestions not only welcomed but implemented throughout the Allied engineering corps. This professional validation catalyzed profound psychological shifts. German engineers witnessed decision-making processes that directly contradicted Nazi propaganda about British inefficiency. Engineering meetings followed a democratic pattern unimaginable in German military culture. Junior officers freely questioned senior officers' approaches. Sergeants with practical experience were invited to critique officers' theoretical designs. Most shocking to German observers, British officers readily admitted knowledge gaps and solicited input from all ranks. Captain Weber's diary, later recovered by military historians, noted his confusion. British engineering teams debate options openly, testing multiple approaches before reaching consensus. This appears inefficient, yet consistently produces superior outcomes to our command-driven process. The technical collaboration created unexpected human connections. British engineer Lieutenant Thomas Bedford recorded in his memoirs, "We began by viewing the Germans as convenient technical resources. We ended by recognizing them as fellow professionals, trapped by circumstance in opposing armies." This evolution appeared in small but significant changes. German officers initially ate separately under guard. By mid-1944, they shared meals with British counterparts, discussing pre-war engineering projects and technical publications familiar to both groups. German engineers were permitted access to British technical journals and engineering manuals. Some began corresponding with British engineering firms regarding post-war applications of Bailey Bridge principles to civilian reconstruction. Royal Engineer Colonel Robert Crawford, who supervised 3 German advisory units, documented this transformation in his March 1944 report to the War Office. The German engineers have undergone remarkable psychological reorientation. They arrived thoroughly indoctrinated in Nazi technical superiority myths. Direct experience with British engineering approaches has systematically dismantled these beliefs. They now recognize that collaborative methods produce more effective outcomes than authoritarian command structures. The Anzio landings in January 1944 further accelerated this transformation. As Allied forces established their beachhead, German engineer Lieutenant Schmidt witnessed American Sherman tanks crossing a Bailey Bridge his team had designed. The cognitive dissonance proved overwhelming, his expertise now directly contributing to German military setbacks. Yet his professional pride in the bridge's performance remained intact. This internal conflict appeared repeatedly in censored letters home. German engineers expressed concern for families while simultaneously recording pride in technical accomplishments that hastened Allied victory. By spring 1944, as Allied forces broke through at Monte Cassino and advanced toward Rome, dozens of German-designed bridges supported their progress. Each structure represented not merely a physical span across Italian rivers, but a psychological bridge between opposing worldviews. German engineers raised in a system that equated strength with hierarchical control, encountered daily evidence that collaborative approaches produced superior results. Every successful bridge adaptation, every implemented German suggestion, systematically undermined Nazi claims of innate German technical superiority. The engineers who had once built Hitler's Atlantic Wall now found themselves literally paving the way for its circumvention. Their expertise respected not for national origin, but for professional merit alone. Summer 1944. Normandy coastline, 3 weeks after D-Day. German engineer Major Karl-Heinz stood atop a recently completed Bailey Bridge spanning the Orne River, watching Allied supply convoys rumble northward toward Caen. The bridge, incorporating his own double-truss modifications, shuddered, but held steady under the weight of Sherman tanks. 6 months earlier, he had been designing defensive obstacles for the Atlantic Wall. Now his expertise supported the wall's systematic dismantling. "Your bridge is performing admirably under loads exceeding specifications," observed British Colonel Mackenzie, who had transported several German engineering officers to Normandy to witness their handiwork in operation. General Montgomery specifically requested I convey his appreciation for the rapid deployment improvements your team suggested. The German officer nodded silently, professional pride warring with national loyalty as he watched vehicles advance toward his homeland. The Normandy campaign transformed the German engineers' psychological journey from reluctant collaboration to active contribution. As Allied forces established their beachhead and pushed inland, they deployed over 380 Bailey bridges, many incorporating modifications designed by German prisoners. Military records document that 17% of all bridging operations in the European theatre by August 1944 utilized specifications developed or refined by German engineering advisory units. These captured engineers, originally seen as mere technical resources, had become essential contributors to Allied mobility. War Office Memorandum WO 2227 U113 noted, German engineering consultants have reduced average bridge deployment times from 8 hours to 5.5 hours through assembly sequence modifications. This 31% improvement significantly accelerates our advanced capabilities. The professional transformation accelerated as German engineers received news of Allied advances. Each briefing about successful bridge deployments across France created profound cognitive dissonance, their expertise directly contributing to German military setbacks. Yet their technical pride remained intact. even intensified by British implementation of their suggestions. Engineer Lieutenant Schmidt's diary entry from July 1944 revealed this internal conflict. Today we learned our modified panel connections were adopted as standard throughout the Allied Engineer Corps. I feel simultaneous professional validation and national betrayal. How can good engineering serve a cause that harms my country? Perhaps good engineering serves truth regardless of nationality. This philosophical questioning intensified as engineers received verified reports contradicting Nazi propaganda. Royal Engineers officers systematically shared reconnaissance photographs and situation reports with their German counterparts, demonstrating actual battlefield conditions rather than filtered propaganda. When German engineers questioned the accuracy, British officers arranged secure telephone communications with newly captured German engineers to confirm conditions. This direct peer-to-peer verification systematically dismantled Nazi information control. By August 1944, many German engineering officers requested permission to write technical corrections to letters they had previously sent home, attempting to counter misinformation their families received through official German channels. The Bailey Bridge itself emerged as the perfect symbol of contrasting engineering philosophies. The German approach, exemplified by massive concrete Siegfried Line fortifications, relied on permanence, overwhelming material investment, and rigid specifications. Each structure required extensive specialized labor, custom designs, and unique materials. The Bailey system represented the opposite approach: standardized, adaptable, rapidly deployable by semi-skilled troops. A standard Bailey bridge kit required exactly 3,000 distinct parts, all interchangeable, allowing infinite configurations from identical components. British production reached staggering levels. Factories in Birmingham, Manchester, and Glasgow produced 700 complete bridges monthly at peak production. This modular approach initially struck German engineers as crude, even primitive. Their subsequent conversion to its advantages represented complete philosophical reorientation. Statistical evidence documented this systematic transformation. By September 1944, Allied forces had deployed 1,500 Bailey bridges in the European theatre, spanning 33 miles if arranged end-to-end. German engineering contributions had improved load capacity from the original 40 tons to 70 tons, allowing passage of the heaviest Allied tanks. Assembly times decreased from the original 8 hours for standard spans to as little as 3 hours for pre-configured sections. These improvements directly translated to operational advantages. Allied forces advanced approximately 15% faster in sectors with German-advised bridge teams compared to sectors using standard designs. Each percentage point represented territorial gains, purchased with fewer casualties. The liberation of Paris in August 1944 provided powerful symbolic reinforcement. German engineers watched newsreel footage of Allied vehicles crossing Seine River bridges that incorporated their modifications. More significantly, they observed French civilians celebrating liberation, directly contradicting Nazi claims that occupied populations preferred German governance. Engineer Captain Weber wrote in censored correspondence, "The Parisians' evident joy forces reconsideration of everything we've been told. If our occupation was as benevolent as claimed, why do they celebrate its end so passionately? This question haunts me more than technical challenges ever did." The psychological transformation reached its zenith when German engineers began receiving news about concentration camp discoveries. British authorities, recognizing the potential impact, arranged for German Engineering Advisory Unit members to receive verified documentation of Nazi atrocities as Allied forces discovered them. Unlike typical prisoners who might dismiss such evidence as propaganda, these engineers had developed trust in British information accuracy through months of verified technical exchanges. The evidence proved impossible to dismiss. Engineer Major Heinz's October 1944 diary recorded his devastation. "The bridges we design now carry forces that will expose horrors committed in our nation's name. I find myself hoping they advanced rapidly. By autumn 1944, as Allied forces approached the German border, the Bailey bridges designed with German assistance had become physical manifestations of ideological transformation. Each structure represented not merely tactical advantage, but philosophical victory, the triumph of collaborative pragmatism over authoritarian rigidity. The German engineers who had begun as reluctant consultants now actively contributed improvements, many explicitly recognizing that accelerating Germany's defeat might be their greatest service to their homeland. Their bridges carried Allied forces toward Berlin, while simultaneously carrying their own consciousness toward profound reconstruction of everything they had once believed certain. Spring 1945. The shattered remains of Remagen Bridge, Germany. Engineer Captain Friedrich Weber stood at the eastern bank of the Rhine, surveying the destruction with professional detachment. The once magnificent structure lay twisted in the water, destroyed by his countrymen in a failed attempt to halt the Allied advance. Beside him, British Major Harrington unfolded plans for a Bailey Bridge to span the same crossing. "We'll need 6 parallel configurations to handle the width," Harrington explained. "Your calculations for the current strength were precisely correct." Weber nodded, the professional acknowledgement now familiar after 2 years of collaboration. 300 meters downstream, American tanks already rolled across a completed Bailey Bridge, designed with modifications he had suggested months earlier. Each vehicle moving toward Berlin represented both his nation's defeat and his own technical success, a contradiction he had ceased trying to reconcile. The final months of European conflict accelerated the German engineers' psychological transformation. As Allied forces pushed into Germany itself, Bailey bridges, many incorporating German-designed improvements, spanned rivers their creators had once been tasked with defending. Military records document 2,141 Bailey bridges deployed in the European theatre by war's end, creating 43 miles of crossings that accelerated Allied advances by approximately 27% compared to predicted timelines. The War Office's final assessment, WO 229-56, concluded, "German engineering consultation reduced bridge deployment times by an average of 41%, while increasing load capacities by 35%. This technical collaboration directly contributed to shortening the European conflict by an estimated 60–90 days." The engineers' return to their homeland delivered profound shock. As Allied forces transported German engineering advisory units into Germany to assist with critical infrastructure repairs, these specialized prisoners confronted destruction beyond their worst expectations. Engineer Major Karl Heinz recorded in his May 1945 journal, "Frankfurt is unrecognizable. The central railway station where I once commuted daily stands as skeletal ruins. Yet 30 kilometers outside the city, a Bailey Bridge I helped design now carries supplies preventing starvation. The irony crushes me. My expertise failed to protect my homeland, but now helps preserve what remains." The contrast between German infrastructure approaches and Bailey Bridge principles became starkly apparent during initial reconstruction. Traditional German engineering emphasized permanence through massive material investment, reinforced concrete structures designed to last centuries. This approach rendered reconstruction nearly impossible amid material shortages and collapsed transportation networks. The Bailey system's modular efficiency, lightweight steel panels requiring minimal equipment for assembly, provided the only viable solution for immediate restoration of essential crossings. Engineer Lieutenant Schmidt noted in his August 1945 assessment, "Our pre-war approach required 340 tons of materials and 145 skilled workers to span 100 meters. The Bailey system achieves the same with 85 tons and 40 semi-skilled laborers in 1/5 the time. Our monumental philosophy appears catastrophically impractical amid our current devastation." This recognition catalyzed rapid adoption of Bailey principles throughout occupied Germany. By December 1945, British authorities had released approximately 420 German engineers from prisoner status to serve as civilian reconstruction consultants. These former prisoners became instructors, training German civilian workers in Bailey Bridge assembly techniques. Their expertise, developed in captivity, proved essential to establishing minimum transportation networks for basic survival. International Red Cross reports from early 1946 credited this program with preventing widespread starvation by restoring critical supply routes before winter. German engineer Captain Weber, appointed regional reconstruction coordinator for Hesse province, implemented 84 Bailey bridges within 6 months, reconnecting communities isolated by systematic demolition during Germany's collapse. The statistical contrast between reconstruction approaches told an irrefutable story. Traditional German methods required an average of 47 days to restore river crossings using conventional techniques and materials. Bailey Bridge deployments, supervised by former prisoner engineers, achieved the same in 3 to 5 days using prefabricated components. By mid-1946, approximately 35% of all functioning bridges in the British occupation zone utilised Bailey components, either as temporary spans or permanent installations with concrete reinforcement. These bridges carried daily necessities to German civilians, supervised by engineers who had spent years helping Allied forces advance against their homeland. The psychological impact of this role reversal proved transformative. Former prisoners who had expected ostracism for their collaboration instead found desperate communities grateful for their expertise. Engineer Major Heinz, supervising Rhine Valley reconstruction, recorded civilian reactions. An elderly woman approached me today after we completed the Oberwesel span. "You betrayed the Führer but saved our village," she said. "We would have starved without this crossing." Her statement perfectly captures our impossible position: national betrayal and humanitarian service simultaneously. This complex reconciliation between national identity and professional ethics shaped the emerging West German technical philosophy. Former prisoner engineers, having witnessed both systems' strengths and weaknesses, developed hybrid approaches that would define post-war German reconstruction. They retained traditional German precision while adopting British modular efficiency and collaborative decision-making. Engineer Lieutenant Schmidt, appointed to the newly established Federal Transport Ministry in 1949, explicitly acknowledged this influence. Our pre-war engineering culture emphasized monumental permanence regardless of cost or practicality. Our captivity exposed us to systems valuing adaptability, efficiency, and collaborative improvement. Germany's future lies in synthesizing these approaches, retaining our technical precision while abandoning our rigidity. By 1950, as West Germany began its economic recovery, bridges stood as physical manifestations of this philosophical transformation. Bailey components, originally deployed as emergency measures, had been incorporated into permanent structures throughout the country. Each hybrid creation represented both practical necessity and symbolic reconciliation. British pragmatism supporting German precision in structures designed by engineers whose captivity had transformed them from enemies to collaborators and finally to synthesizers of opposing traditions. These bridges, spanning rivers their designers had once been ordered to defend against Allied crossings, now carried a recovering nation toward an integrated European future. The German engineers who had begun as stunned captives had become, through their professional journey, unlikely architects of both military defeat and civilian salvation, building literal bridges that simultaneously served as metaphorical connections between past certainties and future possibilities. Summer 1965. Bundesautobahn 45, Siegen, West Germany. Friedrich Weber, now Director of Federal Highway Engineering, stood at the observation platform overlooking the Sieg Valley Viaduct. Below him stretched 1,050 meters of elegantly arched spans, rising 97 meters above the valley floor, Germany's largest bridge project since reconstruction began. Foreign dignitaries and journalists gathered for the opening ceremony, including silver-haired British Colonel Harrington, now Sir David Harrington of the Royal Engineers, who had supervised Weber's prisoner engineering unit 20 years earlier. The span calculations reflect Bailey principles, though you'd never know from looking at it, Weber explained to his former captor. pointing to the seemingly traditional concrete arches. Modular internal framework, standardized components, all assembled in sequence rather than monolithically. Harrington nodded appreciatively. The visible structure speaks to German aesthetic tradition, while the invisible engineering reflects British pragmatism. A perfect synthesis, wouldn't you say? Weber smiled, extending his hand to the man who had once accepted his surrender in North Africa. Like our nations themselves, I suppose. The 2 decades following Germany's defeat witnessed remarkable transformation of both physical infrastructure and engineering philosophy. Former prisoner engineers, uniquely positioned between German technical tradition and British innovation, emerged as intellectual leaders in West Germany's economic miracle. By 1965, approximately 46% of senior positions in government engineering departments were occupied by veterans of British engineering advisory units. Their influence extended beyond government into academia and industry. Of the 8 engineering deans at major West German technical universities, 5 had served in these specialized prisoner units. This leadership generation imported collaborative approaches directly contrary to pre-war German hierarchical models. Engineer Major Karl Heinz, appointed to the prestigious chair of structural engineering at Aachen Technical University in 1954, transformed the curriculum to emphasize adaptability rather than monumentality. His widely adopted textbook, Structural Adaptation Principles, explicitly credited his prisoner experience. My captivity revealed that technical excellence flows from collaborative improvement rather than authoritarian prescription, a lesson that applies to both bridges and societies. The Anglo-German engineering relationship evolved from captor-prisoner to partnership with remarkable speed. By 1950, British and German engineers were collaborating on reconstruction projects throughout Europe. The Joint Engineering Council, established in 1951, formalized this relationship through exchange programs, shared research, and technical standardization. German engineers who had once considered British approaches primitive now sought their expertise in rapid deployment and modular systems. British engineers who had once dismissed German precision as inefficient perfectionism now incorporated German stress analysis and quality control methods. The European coal and steel community, precursor to the European Union, adopted standards reflecting this synthesis, precise tolerances achieved through standardized components. The children and students of former prisoner engineers carried this influence forward exponentially. By the 1960s, Werner Schmidt Jr., son of engineer Lieutenant Schmidt, had established Germany's largest bridge consulting firm, with offices in London, Paris, and Rome. His international staff applied hybrid methodologies to projects on 4 continents. When interviewed for Engineering Review in 1964, he explicitly acknowledged his father's influence. My father returned from captivity with transformed perspective. Our family dinner conversations revolved around technical philosophies, German precision married to British adaptability. I've built my entire career on that foundation. This second-generation impact extended throughout German industry. Companies like Krupp and Thyssen, once synonymous with German militarism, now employed collaborative engineering methodologies introduced by former prisoners who had risen to management positions. Educational reforms institutionalized these changes permanently. The German engineering education system, historically emphasizing theoretical purity and hierarchical instruction, underwent systematic transformation led by former prisoner engineers. Practical problem-solving, team-based projects, and industrial collaboration became curriculum requirements rather than afterthoughts. Technical universities established exchange programs with British institutions, creating formal pathways for methodology cross-fertilization. By 1970, West German engineering degrees required collaborative project experience, a direct legacy of Bailey Bridge construction techniques that prioritized team assembly over individual brilliance. Statistical evidence documented this transformation's practical impact. West German infrastructure reconstruction, initially predicted to require 25-30 years, reached completion within 15 years through hybrid methodologies. bridge construction costs decreased approximately 32% compared to pre-war German approaches, while increasing average lifespan by 24%. Most tellingly, German engineering export contracts increased by 340% between 1950 and 1970, with international clients specifically citing the German technical precision implemented through pragmatic systems as their selection rationale. The synthesis had created competitive advantage beyond either original approach. The philosophical transformation extended beyond technical applications to shape institutional structures throughout West Germany. Former prisoner engineers, having witnessed British collaborative decision-making, applied similar principles to organizational design. Engineer Captain Weber, appointed to the Federal Transport Ministry's Reorganization Committee in 1952, explicitly incorporated matrix management principles observed in Royal Engineers operations. His influential report, Organizational Efficiency Through Collaborative Structures, rejected both rigid German hierarchies and chaotic improvisation in favor of structured collaboration with delegated authority. These principles shaped dozens of public institutions, systematically replacing authoritarian models with collaborative frameworks that maintained German precision while incorporating British adaptability. By the 1970s, as Europe moved toward greater integration, bridges designed by former prisoners and their protégés physically connected the continent in ways that seemed impossible during wartime. The Rhine bridges linking Germany and France, the Alpine spans connecting Germany and Austria, and the landmark Fehmarn Sound Bridge joining Germany and Denmark all incorporated Bailey-inspired principles implemented through traditional German precision. Each structure represented both practical transportation and powerful symbolism. Former enemies now literally connected through hybrid engineering that transcended national boundaries. The most profound legacy emerged not in physical structures but in philosophical transformation. The German engineers who had begun as stunned captives evolved into architects of reconciliation, applying technical lessons to social reconstruction. In his retirement address to the Federal Engineering Association in 1975, Friedrich Weber articulated this journey. We began as prisoners faced with an impossible request: to apply our expertise against our nation's interests. We discovered that true expertise transcends national boundaries, serving universal principles rather than temporal authorities. Our greatest bridges weren't built across rivers, but across divided conceptions of how societies function. We learned that strength comes not from rigid hierarchy, but from structured collaboration, not from imposed uniformity, but from diverse perspectives united by common purpose. The bridges constructed from this philosophy would ultimately support not just reconstruction, but the peaceful reunification of a continent once shattered by conflicting certainties.